In 1805, Admiral Lord Nelson changed naval warfare forever. This is how naval warfare used to be: two fleets opposed to each other, firing point blank until one gives up and retires from the field. But that all changed in 1805. At the Battle of Trafalgar, Lord Admiral Nelson ordered his entire fleet to dive straight at the enemy. You know what happens when you send one fleet into another in naval warfare? A hot mess. Chaos ensued. Friend and foe mixed together. It's hard to know what to do when. Which is why Nelson invented an innovation authentication method for this battle. He painted all of his ships in this black and white paint scheme. And that worked great because of two reasons. One, it was accurate. Only his ships were painted like this. And it was easy to use. At a single glance, every ship, every crew, every sailor could instantly see friend or foe and take action. But immediately after the battle, challenges started to arise to this technique, right? As various navies started impersonating the paint scheme, causing accuracy issues. And actually, it was too easy to use, right? As soon as an opponent knew the scheme, they could use the same thing, and the single glance would give them the same information. You couldn't restrict it to only those people he wanted to be able to use his method. Now, facial recognition in the last decade or so has been on a similar curve. It's accurate and easy to use when it works well, right? A single glance has given us authentication, and paired with the rise of mobile devices, that's a very powerful combination because it's not out of band, right? What do? You pick up your phone, you look at it, and instantly you're strongly authenticated locally to that device, which can drive other innovations, such as serving underprivileged populations who don't have as much access to financial products or insurance. And with facial recognition on board, that can give them access to new types of infrastructure. But just like the Nelson checker, this innovation's facing challenges. We've seen issues with accuracy and bias being revealed. And in fact, it's too easy to use. There are problems with just restricting facial recognition and to those people that you want to do it on your behalf. Over the last several years, the Algorithmic Justice League has shown, along with the NIST and others, that there is bias in these algorithms and these models, that minority populations are underserved and they are discriminated against as a result. And that bias is fine on its own and problematic on its own, but it's even worse when governments and law enforcement start to take it and wield it as part of their process. Russia, China, the UK all have CCTV systems that can use facial recognition to monitor citizens. Australia is using it for COVID-19 tracking, and the US government law enforcement has used video surveillance alone to arrest at least no fewer than 3 Black male suspects. Now, with that bias baked in, that becomes particularly dangerous. And then there's the other side, right? The ease of use, being too easy to use. In the last year or so, we've learned that there are companies who are going out and taking photos that people have uploaded to Facebook, Google, Instagram, and scraping those off and building their own repository and then selling facial recognition databases that result to law enforcement. It's hard to keep just those who you want to have access to it. And even if they're not selling it to law enforcement, anyone keeping a database of facial information is under danger of a breach, like the Customs and Border Patrol had happened in 2019 in the United States. Now, governments and legislatures are trying to catch up, right? The United States has the state of Illinois has a law preventing biometric misuse of data. And Canada and Sweden, among other countries, are working to make sure that organizations such as Clearview AI are not allowed to operate in their jurisdiction. But that's more reactive, right? What this calls for, if our ethics are to be defended, is something a bit more proactive. And that's where adversarial research comes into play. Now, over the past several years, we've seen adversarial research address the issue of bias, right? To figure out where it's flawed, where the model is flawed, and improve that accuracy. But in the last 6 months to a year, there's been a whole adversarial research expansion into the ease of use aspect, trying to restrict facial data, facial recognition to be used only by those that people authorize them to do. In other words, providing some individuals some kind of agency, even as they upload their photographs or their snapshots to these social media sites, to give them some form of protection against misuse. And that's what we'll talk about today. We'll explore the latest research, the pros and cons of how they work, and then we'll introduce an open source proof of concept mobile app that uses some of these techniques to do just that, to give people some agency in protecting their own privacy. Now, looking back at the adversarial approach that have taken place, this kind of started somewhat back in 2001, where there was a geometric approach where it changed pixels within these photographs and thwarted facial recognition. This worked surprisingly well. It was cheap, it was fast, but it was static, and facial recognition quickly caught up in the cat and mouse game that is adversarial research. Then came generative adversarial networks, which are actually two different machine learning models that are competing and kind of working together. There's the generator and the discriminator, right? And the generator is creating face-based images that is trying to make as real as possible. And then the discriminator, which has been trained on real images, is trying to differentiate between the reals and the fakes. These compete with each other, and it's a feedback loop. You get more and more realistic images, and you get things like these. You may have seen this on thispersondoesnotexist.com, and the high-level attributes are retained, the low-level attributes are modified. These are wholly synthetic people, often, and this works pretty great, except for a few problems. One, it's static. In other words, you could use this as your avatar, as your replacement face online, but then it would be one-to-one tied back to you, and you'd be back to square one. The protection would be static, and it's expensive. And you require processing power that you may not have, and it wouldn't be as easy as on a, say, Face ID on a mobile device. Now, July of last year, researchers from Australia introduced Camera Adversaria. And what this does is it takes images and it introduces procedural noise, natural looking noise into an image, and it disturbs the classification system. It's an Android app, it's a camera app, and so it's in the flow, and it like I said, it perturbs the classification. Let's see this in action.
The Camera Adversaria app is an Android app, obviously, that uses the on-device camera. Taking a photo, or as in this case, selecting a pre-existing photo from the dedicated collection, results in the image being displayed in the main view. A classifier runs on the device itself, MobileNet-based, and gives the top classification of the image. Simplex noise is applied in a filter via the GPU image library, and then the object is reclassified after the image is redrawn. Here you can see that by moving the slider to a higher setting, the noise begins to reveal itself from the image, and distortion results. A leatherback turtle, chainmail, and other options are identified as the noise affects the classifier and the top result changes due to the perturbations.
So that's a great approach. It's quick, it's simple, it's direct, it's a mobile app. Around the same time, a new method appeared from the University of Chicago, and this was called Fox, after Guy Fawkes. And what this does is it takes your original images that you've taken or that you have, your faces, and then it combines them with a collection of faces from a particular target, a different individual that's not you. The feature sets are combined, you have cloaked images, which are then made available to these facial recognition systems, which take them in as training data. And then when your real photos are out there, it misclassifies you as the target individual. It uses a loss function to optimize. It's a Mac and Windows application that's been open sourced. And so what you kind of have to do is you have to either download the binary or download it and compile it yourself. So there's a bit of a usability issue. But let's take a look here. And what it actually does, as I said, is it tries to shift the feature set so that your feature set actually gets intermingled and misidentified and classified wrong. Keep in mind that kind of like the Perlin noise option, what they're trying to do is modify the photo so to a human it looks realistic, it looks normal, but to a facial recognition system, it presents great difficulty.
It's always helpful to see these tools in action, and so I'm going to use the IntelliJ IDE, and I've downloaded the Fox open source tool, and we'll look through the code, see kind of get a sense of what it's doing, and then we'll actually see it in action and what it produces over time. Most of the actual meat of the tool takes place in this Fox object, of course. It's got some initialization, looking for GPU, setting up TensorFlow. The tool is designed for TensorFlow 1, and so you'll see a lot of backwards compatibility in the TensorFlow commands. Note that what it's going to use to detect the faces and for feature extraction and some of the comparison is MTCNN. Of course, it's that multitask cascaded convolutional neural network, mouthful, which is why they have the acronym. And then, of course, the tool has multiple levels from min to ultra, and this impacts how dissimilar the resulting image, how much protection is embedded in the final image. It's setting things like the similarity threshold, which is that TH variable you see there, and then the step size and the learning rate for the training that will take place. What it does first is it goes ahead and detects the faces, crops them, aligns them if it's desired. It doesn't have as much of an impact as you might think, so the alignment is turned off by default. Once it gets those images, it's going to go through and find the target embedding for all of those images and kind of batch them up together. Because what it really wants to do is it wants to go and find what target to use. And what it's doing is it's looking for another image and use that other image's feature set and make the image that you want to protect or the face that you want to cloak, make the feature set result be a lot more similar to the feature set of that target image. And so to do that, it actually calls the select target label. And so what it does is it goes out and it picks out a random set of potential images from a hosted data set out on the University of Chicago's servers. And what it does is it measures a distance for each of them that is most dissimilar to all the target images taken as a whole. Then it actually goes ahead and sets up the protector. If we go look at that, it's got the variables in here. It is also converting things to 10H space. And then down here, it's using DSSIM to do the difference, the user perceived difference between the real image and the modified image. And so what it's doing, that's the structural dissimilarity index. And so what they're trying to do is they are taking it so the images are different than what they originally were, especially to the machine vision aspect, but then not so different that you look like a totally different person to a human. And so what they're going to do is they're going to set up their losses down here that they're going to, optimize using an Ada Delta stochastic gradient descent method. And basically they're baking into that loss that human perceivability component to make sure they're not too far afield with the resulting image. So after all that takes place and everything is set up, actually the attack method is eventually called, and that basically sets it up to where it's going to go through each of the images in turn and generate a cloak, hand that off to attack batch, which is actually going to do the actual session and the training. And so what results is you get a set of images that have modified faces that are trying to protect those faces from facial recognition, obviously. And eventually the faces are merged back in, and they're labeled, and they're written out. Now I'm going to go ahead and run the tool on the minimum level just to give you a sense of what it looks like and how it goes. And so when we run it, well, you see it load up, and then what it will first do is it will go and find the images that it wants to protect, which is in a default directory. So the way you would do this is you would run it on images that are already on your hard drive and then apply the cloak protection and then upload those, which is kind of inconvenient, and it's just why we made a mobile app for the other. You can see it find the target that it wants to use to shift the feature set. You can see it here setting up the mask generation function to set up the TensorFlow information and the functions it's going to use. And now it starts to go through each of the images, and it's training. It's developing a cloak, and I'm applying that cloak for one image at a time. And we'll go ahead and speed this up so we don't have to watch the whole thing. So you can see it took about 83 seconds to do those 4 images, and this gets a lot longer depending on the quality of cloaking or how much, what level you want to defend your images. Looking at what those images actually look like, we see the original image that's unmodified, and then we can cycle through, and you can see that, the minimum image has a little bit of modification, especially around some of the features, but it's, especially in small format, it's not that noticeable. This one took 88 seconds or so, about a minute and a half. When we flip up to low protection, you see the artifacts start to get stronger, and this was almost a 3-minute runtime. When we go up to the mid-level of protection, now you're talking in the order of 10 minutes for 4 images in this case, but it still kind of gets prohibitive. And then, of course, the high level modifies it greatly. I kind of resemble a cartoon villain from the old days. And for 4 images, it took 22 minutes, so like 5 minutes per image on the top level. Usability then is a key problem here, because that's going to, not only do you have to download the tool and run it, but it's a time-consuming process.
Looking at the effectiveness as Fox, larger numbers here are better, obviously. They tested against the 3 large facial recognition systems, Microsoft's, Amazon's, and Face++. And you can see they did the best against Microsoft's. Now, it's a balance between usability and protection. And in January, it should be noted that the authors went back and noticed that the data has changed against Azure, and they think that Microsoft may have trained their model slightly to improve its defense against something like Fox. Now, at the same time, Loki was being worked on, and this was from the University of Maryland. It was announced earlier this year. It'll be presented in May. It's using a similar process to do an adversarial attack on image, pollute the training data. It uses a slightly different loss function, and one that incorporates not just detection, not just classification of the image, but also detection, the whole process. Keep in mind that this is not open source. It's a hosted web service where you submit your pictures and then you get them emailed back to you. So it's kind of out of band. The effectiveness, it's important to note that here it is lower numbers that are better, because what they're doing is they're using it like law enforcement would. In other words, they're not doing a one-to-one match. They're looking and saying, I've got this image of a suspect that I want to know who it is. Return to me the top N suspects that I need to go and investigate. And so you can see that Loki has a higher resolution and it performs better with their algorithm and their testing than Fox did. Now, looking at all these, you can begin to categorize and summarize some of them and their different approaches. And the open source app that we're going to propose tries to use the best of all of these worlds. We want a mobile application format because that helps with ease of use, right? If it's not on a phone, people won't use it. If it's not in the flow of taking a picture, people won't use it. Along with that, we want dynamic protection. We want a protection for each image on its own, not just a static approach that can be countermanded. We want it to look like the person to a human to be useful. We want it to be cheap because of that mobile format. And then ideally, we want to protect against not just classification, but also detection, the other part of facial recognition. And so that's what we're doing. We're building a mobile app here that tries to be useful. It's usable as a camera app to normal people, which also means that we're limited to mobile, which means that we don't have TensorFlow. We only have TensorFlow Lite, which means that training is very limited for now on mobile devices. And we're going to release this on GitHub. But again, for usability, we would push this like the Camera Adversarial app into app stores for download and usage. The flow of the application is in 3 phases. The first is we'll take the image and we'll apply a style to it using arbitrary fast style transfer. Once we have the stylized image, then we'll inject some procedural noise to disrupt the classification. Then we'll have a final image and we'll do a sanity check to see how we're doing against facial detection and recognition. And then we will save it to an album or allow the user to upload it from there. The first phase is arbitrary fast style transfer. What this does is it applies a style to a content image. You have a content image and a style image. And actually 2 different inferences run. The first is a style prediction model, which has been trained on other styles. It extracts the top layer of that model into a bottleneck. And now you have the style from that style image, which you can then apply on the content image with the style transform model. It's kind of like a paint by number technique. Now, if we run both the style image and the content image through that first style prediction model, now we have the styles of the style image and the content image, and we can begin to play with it and choose how we want it to appear in the final image.
We're going to use a Jupyter Notebook to show you the algorithmic flow that takes place as we go through the core of the open source app that I've developed. And so really here what you can already see is we're just importing the table stakes, right? Python 3.8 and TensorFlow 2.4. In the actual iOS app, of course, we'll be using TensorFlow Lite, and we'll use a nightly build with the metal parameter to make sure we can get the GPU acceleration on the iOS app itself that we're building in Xcode. Next step is to include a couple of libraries that will be helpful to do some math, some time calculations, so forth and so on. Some of these will be available in Xcode, not all of them, so some of it we'll have to do some hand rolling of functions ourselves. What we'll also do is we'll go out and grab a couple of things for the demonstration. The first is the face, the picture of the person that we want to manipulate, to seek to protect in an adversarial fashion. And the other is the style that we want to transfer onto that person's face. And then finally, we will go and get both the prediction model as well as the transfer model. Both of these have been trained, and we'll use these. Since we have a GPU available to us on iOS, we'll use a Float 16 version of these, and that will give us a faster transfer. Note that the style and the models are all resident in the app. There are a couple of sample faces on the iOS app, but also you can use anything from the camera roll, and you can also just take a picture live as you normally would. So the next step is to pre-process the images that we want to use, both content and style, to prepare them for the model. They need to be RGB images with pixel values being float 32 numbers between 0 to 1, and a particular size. The style image has to be 256 by 256, and the content image must be 384 by 384. Luckily, TensorFlow gives us a lot of these methods already. Like for example, the decode image you see there, and converting images between data types. Some of these will be available, but a lot of these we'll have to use with Swift's own UI handling and graphics processing. Finally, we print out the shape of the images just to make sure we're ready to go and they're ready to be used with the model. And you can see the appropriate shape there that the models expect. The next step here is just to print out or visually display in the notebook the content and the style image that's been pre-processed. Just make sure it's a sanity check, make sure it looks like we think before we actually run them through the model. The next step is pretty straightforward. What we do is we take our pre-processed style image and place it on the input tensor for our style prediction model. We run it through the model, we run inference on it, and that reduces that style image down to a bottleneck that we can use in our transfer model to apply that style to our content image. Now that we have our style bottleneck and we already have our preprocessed content image, we can now feed these into the input tensors for our style transform model, and we actually get a stylized content image. It's 384 by 384 as a result, and it was relatively fast, which is what we're looking for. And that's good, but we can do better, because if we run the content image that's been pre-processed through that style predict model, we can also get the bottleneck for the content image. And then if we have the bottlenecks for the content image and for the style image, now we can play with the ratio between those two and decide how much style input we want and how much content input we want. And we can have a whole range of stylized images, from very, very dislike the original to very, very close to the original, albeit slightly modified. And this is what's going to give us the dynamic filter effect, that every time you take an image and you stylize it, not only are you changing the style that you're applying, but you're also changing the impact of that style, which means you have different and a wider variety of resulting images. And you can also adjust the strength of that filter until it provides the protection that you're looking for the image that you have just taken or are concerned with.
And here you can see the range of styles and how it applies and the impact it has as you shift that slider that you'll see here in the demo in a bit. Now, the app is designed to be isolated mode. In other words, you don't need to be on a network. And so there are 32 onboard styles. If you do happen to be connected to the internet, then you have 80,000 more styles at your disposal to download and use. The more you rotate these, the more dynamic the protection will be. The phase 2 is procedural noise generation. And this is where we're going to, like the Camera Adversaria app, inject noise into the image. And we're using simplex noise because we know it impacts classification. It's relatively computationally cheap. It's dynamic and can be uniquely generated for every image. And if you do it right, it's not that obvious to the viewer. And we can just use GPU image to apply this filter. And there's an open source algorithm, so it's fairly straightforward. Then phase 3 is evaluation. We check to see how we've done. We look, in this case, for facial detection using Google ML Kit, just to see how it has protected or not.
And now for a quick demo of the current open source app. Currently, the app is installed on the iPhone through Apple's Xcode application, but long term, my hope is that it will be available for free from the official App Store. Now, just to orient you to the app interface a little bit here, the top row allows you to cycle through a sampling of faces to modify with the next image link there. The option of selecting an existing photo from your camera roll, or to take a new photo with the built-in camera facility. The video icon you see there is for future use, but it's not supported at this time. The center view shows you the current image you're working with and its current status, and the middle tabs just beneath that allow you to cycle between the original photo, the style that you're applying to that original photo, and the images that result from the style transfer and the resulting simplex noise perturbation that's injected in, which you shouldn't be able to see in most cases. The style, I will note, is also displayed at the square at the bottom right with a change button you'll see here in action in a little bit that will let you select styles. Now, there's also a sliding scale right next to that style image that allows the user to adjust the impact between the original content image and the style image as it is applied. More like the style image, more like the original content image. You can slide back and forth, and once you apply the style, you'll see that impact. There's also a toggle switch to use or not use GPU acceleration. And this is a relatively recent addition to TensorFlow Lite. And for performance reasons, obviously, it's best just leave that on, but it's there just for comparison's sake. Finally, at the bottom, there are buttons to left to right obfuscate the image, by which I mean apply the style, the option to detect faces or attempt to detect faces with Google's ML Kit, to clear any facial detection markings that you may have caused to appear on the image, and finally to save the current image as it's viewed to a dedicated album in the photo roll for the device. Let's run through a sample use case with a phone in the local park set to airplane mode, disconnected from the internet. The user starts up the app and then selects to take a new photo. Keep in mind, by the way, that the same process after image capture would apply to a photo selected from the device's photo roll. It's a rather handsome devil, if I may say so myself. Now, after he's captured the image, you should already notice that the app has center cropped the image in preparation for pre-processing. It's going to be adjusted down to 384 by 384 format eventually, so it's less jarring for the user to go ahead and convert it now to the square format at capture time. At this point, the user can opt to change the style that they wish to apply. It's good to switch this up regularly to make sure each image has a unique protection. At any point in the process, the user can opt to detect faces with the onboard detection feature. Not surprisingly, the unmodified face from the photo is easily identified. The user clears the face detection markings and moves the slider up to be highly stylized by the style image. This protects the image at the potential cost of human intelligibility. It is clearly modified. Running face detection again, however, shows that the face in the image has now avoided detection by Google's algorithm. The user can then adjust the slider, judging for the best combination of protection and usability for their particular use case. Shifting the slider closer to the content image results in the face being detected once more. Note that the app only provides an evaluation of face detection evasion. Later versions hope to include an estimation of how well a face can avoid classification after successful detection. Finally, users can opt to save any of the images appearing in the center view, particularly the ones that have been stylized, to the system's photo roll. The images are placed into a dedicated photo album, thus ensuring that the end user can trust that the photos that they choose to upload to social media or other online services have some measure of protection.
So let's talk about that protection and how well it performs. This is not a rigorous testing like you saw with Fox and with Loki. This is 50 individuals taken from PubFig, a publicly available database. And you can see that as you up the impact the style has, facial detection, faces are actually just not detected eventually over time at the compromise of some usability or human intelligibility, obviously. Classification, in other words, is it identifying the person as the right person? Again, the same kind of 50 small sample data set, and it's a little bit more spread out. The perturbation and the style does have an impact. More formal testing is necessary, and we'll talk about that in just a minute. But at least this is proof of life that shows that both detection and classification are impacted. And so the project is worth pursuing further. And that's really brings me to my next point, which is the future plans here. Formal testing is required, obviously. With probably the face scrub data set, we can test against the big three, Microsoft, Amazon, and Face++. In addition, it would be helpful to have on board the device, not just a test for face detection, but one for face classification. We could use a mobile NetV2 based model, kind of train on your own personal face and to know how far off you've gone from it classifying you correctly as kind of a smoke test. We also need to make scale adjustments to that procedural noise. So you can choose, just like the Camera Adversary app, how much impact it should have. Ideally, we could do a higher res capability. You've seen the images, they're smaller. Long-term, we may be able to stitch together larger pieces. And then finally, there are things like WebAssembly, where you can offload some of this work to, say, a secure enclave, where you could do some of that processing and offload some of that mobile work. So you could do some of the more complex applications like Fox or Loki and the like. You should be asking yourself at this point, Mike, is this practical? To which I'd say yes and no, right? And on one hand, no. Consumers are still limited by those mobile devices. And as a result, the quality is limited, performance is limited, and quality is part of ease of use, right? If I don't get an image that I think looks like I want it to look and show the world, I'm not going to use it. If it's not as easy as just looking at my phone or going through whatever normal process, I'm not going to be as invested as a normal person in protecting my own privacy and my own facial data. So there's work to be done there. And on the other hand, yes, some of these techniques could be used by organizations and enterprises to protect the facial data they have. Much like hashing private data, you could apply masks, you could apply cloaking, you could apply procedural noise to these images when they're at rest. So you could remove it, use the images, and restore them. And this would provide some measure of protection for individuals if you happen to have these facial biometric data in your data set. Regardless, it's a team sport, right? It's not just organizations and enterprises. It's not just individuals. And what this project is doing is trying to give individuals agency to participate in the overall process. And so as you leave today, what I'd like you to think about is what facial recognition use cases you have going in your organization. Whether you're outsourcing it or keeping it internal, contemplate how it's being used and the ethics behind that. Over time, in the next few months, think about potential protections you might be able to either ask for or apply to your facial biometric data, whether it's your customers, your clients, or your employees. This might be particularly of interest to those organizations involved in with avatars or social media, but it also could apply to things like an employee directory that is vulnerable, susceptible to theft or misuse. And then within a time frame, 6 months to a year, start working on and putting those protections in place. Because like I said, this is not just one organization's job. It's not just one individual's job. It's everyone's job. And if we're all pulling together in the same fleet, so to speak, then we can raise the signal just as Lord Admiral Nelson did as he sailed, into the Battle of Trafalgar, where he raised the flag and said, "It is expected that every person will do their duty." Every organization enabled, every enterprise enabled, every individual enabled to invest in privacy. And that's the only hope we have of our ethics not being outstripped by new innovation and new technology like facial recognition. Thank you.